Hello guys, welcome on Tesla Adventures. In this video today, we are going to discuss the concept illustration problems of type 4 and which are based on the problems of pistons. Now in the first question you can see that there are two identical vessels A and B which contains equal amount of an ideal monatomic gas, and this gas is same gas, and piston A is fixed and piston B is free to move. If same amount of heat is being supplied to both gases A and B, it is observed that the internal energy of the B increases by 100 joules. So we have to find out the change in internal energy of A. So first of all, let us analyze the situation that A is going through a isochoric process because its volume is constant, and B is going through a isobaric process because its pressure is constant. You can see that this piston is not movable and it is rigid, so the volume of gas A is constant, and this piston is movable, but outside pressure is obviously atmospheric pressure, which is constant. So we can say that this piston is moving against a constant pressure, and therefore the pressure of this piston will always be, the pressure of the gas below the piston will always be P0, because this process is a quasi-static process obviously. Now if this is an isobaric process, and we know that in isobaric process the heat supplied is equal to dq is equal to du plus dw, and du is obviously 100 joules, and du is the change in internal energy of this gas, and du is ncv dt, which is equal to 100 joules. So you can see that Cv for monatomic gas is 3/2R, so n into 3/2R dt is equal to 100, and therefore nR dt is equal to 200/3. And now if we check out this process, then in this process the heat supplied to the gas is equal to du completely, and the heat supplied in both of them is same. So if we calculate the heat supplied in the second process, then dq will be equal to ncp dt, and in this process n and cp is 5/2R because it is a monoatomic gas, so 5/2R and dt. Now we know that nR dt is 200/3, so this value will be equal to 5/2 into 200/3. So you can see that it would be equal to 500/3. So heat supplied will be 500/3, and therefore the change in internal energy of the gas A will be 500/3. So the correct answer is B. Now we move on the next question. In this problem you can see that there is a monoatomic ideal gas that is filled inside this cylinder, and there is a horizontal piston which is movable, and it is connected to a spring on the other side. Initially the gas was at temperature T1, pressure P1 and volume V1, and the spring was in relaxed state. Now this gas is heated very slowly to the temperature T2, pressure P2 and volume V2. Now during this process the piston moves out by a distance of x. So ignoring the friction between piston and the cylinder, we have to choose the correct option. Now we can see the situation that if the initial pressure is P1, volume is V1 and temperature is T1, and the spring was in relaxed state, then obviously we can say that at this side the pressure, volume and the pressure of the gas would be same, obviously because this piston is in equilibrium and this spring is relaxed. Therefore we can say that the air pressure at this side and this side, the pressure of the gas would be same initially. So we can see that if this piston will move to this side, then first of all we know that number of moles will remain constant, and therefore we can say that P1 V1 by T1 will be equal to P2 V2 by T2. This is the first equation. Second equation is the energy stored in the spring. So you can see that the displacement of the piston is x, then x would be V2 minus V1 by area. Okay, because if initial volume of the gas is V1 and final volume is V2, then the distance moved by this piston would be V2 minus V1 upon area. So the energy, or we can say that obviously this piston is moving very slowly, so this piston would be in equilibrium at all the time. Therefore the pressure of the gas will be equal to the pressure of air this side and the spring force per unit area. So we can write down the equation as P2 of the gas will be equal to P1 plus Kx upon area. So Kx is equal to P2 minus P1 upon into area, and K from this equation will be equal to P2 minus P1 into area by x. This is the value of K. Now first of all we have to find out the energy stored in the spring if V2 is equal to 2V1. So in the first option V2 is equal to 2V1 and T2 is equal to 3T1. T2 is equal to 3T1. So we will use P1 V1 by T1 is equal to P2 V2 by T2. So P1 is P1, V1 is V1, T1 is T1. P2 we have to find out. V2 is 2V1 and T2 is 3T1. So cancelling out this T1 with T1 and V1 with V1, P2 will be equal to P1 by 2 into 3. So this is P2, and V2 and x will be V2 minus V1 by area. So x will be equal to V1 by A because V2 is 2V1. So if we substitute these values, then we will get the K as P2 minus P1 A by x. So K will be P2 minus P1 into A by x. So K will be equal to P2 minus P1 will be P1 by 2 and A by x, and the value of x is V1 by A. So K will be P1 by 2 A by V1 by A. So it would be A square, and the energy stored in the spring will be half Kx square. So U will be half K will be P1 by 2 A square by V1, and x square will be V1 square by A square. So cancelling this, U will be equal to P1 V1 by 4. So the energy stored in the spring will be P1 V1 by 4. So A option is the correct answer. Now in the second option we have to find out the change in internal energy if V2 is equal to 2V1 and T2 is equal to 3T1. So let us use different ink. So in the second option T2 is equal to 3T1. So if we find out the delta U, then delta U will be N CV delta T, and delta U will be equal to N and CV will be 3 by 2R because this is a monoatomic gas, and delta T is 2T1. So delta U will be equal to 3nRT1, and nRT1 is P1 V1. So delta U will be equal to 3P1 V1. So second option is also correct. Third option is that if V2 is 3V1 and T2 is 4T1, then work done by the gas. Now in third option, let us use the different page. We know that in the third option it is given V2 is 3V1 and T2 is 4T1. So V2 is 3V1 and T2 is 4T1. So if we will use P1 V1 by T1 is equal to P2 V2 by T2, then P1 V1 by T1 will be equal to P2 V2 is 3V1, T2 is 4T1. So P2 will be equal to 4 P1 by 3, and the value of K is P2 minus P1 by X. So K will be equal to P2 minus P1, which is P1 by 3 by X, and I think into area, yeah, and the value of X will be equal to V2 minus V1 by area. This is the value of X. So X is V2 minus V1, which is V2 minus V1 is 2V1 by area. So value of K will be P1 A square by 3 into 2, 6V1. This is the value of K, and the energy stored in the spring is half K X square, and X square will be 4V1 by A square. So U will be equal to 1 by 3 P1 into V1. This is the value of energy stored in the spring, and the work done by the gas will be equal to the sum of work done against surroundings plus work done against spring, and the work done against spring is half 1 by 3 P1 V1, and work done against surroundings will be P1 into delta V, because the pressure of the surroundings is constant. So it would be P1 into delta V will be 2V1. Okay, so the total will be 1 by 3 plus 2 P1 V1. So it would be equal to 7 by 3 P1 V1. So the work done by the gas will be 7 by 3 P1 V1, C option. And the heat supplied to the gas, if this in this case, so you can see that heat supplied will be equal to Q will be equal to work done plus delta U. Now delta U will be equal to N. CV is 3 by 2R, and delta T is 3T1. So this is 9 by 2 NRT1, which is P1 V1. So if we will sum up these two energies, if we sum up to find out dq, then dq will be du plus dw. So du will be equal to 9 by 2 P1 V1 plus dw will be equal to 7, in fact dw will be equal to 7 by 3 P1 V1. So this is not the D option, so obviously the correct answers will be only A, B and C. Now we move on the next question. In this question you can see that there is a cylinder in which there is a rigid partition. This is a rigid partition, and this partition is not movable, but it can allow the slow transfer of heat through it. The above chamber contains 2 moles of an ideal diatomic gas, which is at temperature 400 Kelvin. This contains 2 moles of ideal diatomic gas at 400 Kelvins, and the lower chamber contains 2 moles of an ideal monoatomic gas, which is at 700 kelvins. Okay, and we have to find out the equilibrium temperature of these two gases when equilibrium is reached. You can see that if this piston is rigid, then we can say that this gas will exchange the heat at constant volume, and as this piston is movable, this gas will exchange the heat at constant pressure, because when this piston will slowly move out, then the pressure outside the piston or outside the cylinder will be constant atmospheric pressure, and therefore the pressure inside the cylinder, which is the pressure of the gas, will remain constant. So we will say that the heat given by this gas will be N CV delta T, and heat absorbed by this gas will be N Cp delta T. So the heat given by the lower gas will be 2 CV. CV will be 3. In fact, the lower gas is a monatomic gas, and which is at 700 Kelvin, and the number of moles are 2. So lower compartment has a monatomic gas which is having CV as 3/2R, and delta T, let us suppose that the equilibrium temperature is T. So T will be less than 700 and T will be greater than 400. So we can say that for the lower gas, delta T will be equal to 700 minus T, and N is 2, CV is Cp. For the upper gas, diatomic gas, will be Cp will be 1 plus F/2. F is 5 for diatomic gas into R, so it will be 7/2R. So this is 7/2R, and delta T will be, I'll write it down here. So this is 2 into 3/2 R into 700 minus T is equal to 2 into 7/2R into T minus 400. So cancelling out this with this, this is 2100 minus 3T will be equal to 70 minus 2800. So 10T will be equal to this is 2100 plus 2800, so it would be 4900 and T will be equal to 490 kelvins. So the correct answer will be option D. Now we move on the next question. In this question, you can see that there is a fixed thermally conducting cylinder. This is a thermally conducting cylinder, and the radius of this cylinder is R, and the length of this complete cylinder is L0. The cylinder is open at the bottom and has a small hole at its top, and a piston of mass M is held at a distance of L from the top surface as shown, and the atmospheric pressure is P0. Now this piston is pulled out slowly, and it is held at a distance of 2L from the top while this hole opened, and we have to find out the pressure in the cylinder between its top and the piston. So this is quite obvious thing that when this piston will be pulled out, then this hole is open, and therefore the passage of atmospheric air would be easily through this hole inside the cylinder, and therefore the pressure inside the cylinder would be P0. So we can say that the pressure will be P0. So the correct answer of this question is A. And while this piston is at a distance of 2L from the top, this hole is now sealed and piston is then released. Now let us draw the scenario that this hole is being sealed and the piston is at a distance of 2L from the top, and initially this pressure is P0, and now this piston is released, and it is released till it stays in equilibrium. So in the condition of equilibrium, the distance of piston from the top will be. So obviously we can say that at the bottom of the piston the air pressure will be P naught, and finally when the piston will move out, let us use another page. In the final equilibrium position, if the distance of piston from the top is x, then we can say that the pressure or mg will be acting in the downward direction, and the atmospheric pressure will be acting like that, and the pressure inside this gas will be P naught, P, which is something else, and pressure outside the piston or outside the cylinder is P naught. So we can say that the value of P plus mg by area, P is acting in the downward direction and mg upon area will be equal to P naught. So P will be equal to P naught minus mg by area. This is the final pressure, and final volume V final will be equal to x into area, and the initial volume V initial was 2L into area, and initial pressure was P naught. So we have already seen that this cylinder is a insulating, or this cylinder is a conducting cylinder, which means that this process would be isothermal process, and we can use the characteristic equation of isothermal process, which is P1 V1 is equal to P2 V2. So P initial is P naught, V initial is 2L into area, P final is P naught minus mg by area, and V final will be x into area. Cancelling A with A, so x will be equal to P naught into 2L upon into area. This is 2L into area divided by P naught A minus mg. A is pi r square, so you can see that the answer will be P naught into pi r square into 2L upon pi r square P naught minus mg. So the correct answer will be D. Now we move on the next question. In this question, you can see that there are two cylinders A and B, which are fitted with pistons of same cross-sectional area S, and the cylinder A contains m gram of an ideal gas at pressure P and temperature T naught, and cylinder B contains an ideal gas at same temperature T naught, but the mass of the gas in B is different. Now the piston is held at the position in which the volume of the gases in cylinder A and cylinder B is equal, and it is equal to V naught, while the walls of the cylinder A are thermally insulated, which means that the process occurring in the cylinder A is adiabatic process, while the cylinder B is maintained at a temperature of T naught by the external reservoir, and this complete system is in vacuum. So these pistons are released from the initial position, and it is found that they move towards left, and when the mechanical equilibrium is attained, then the volume of the gas in cylinder A becomes V naught by 2. Then we have to find out the mass of gas in cylinder B. First of all, let us see that the pressure of the gas in cylinder A is initially P, volume is V naught, and temperature is T naught. And the pressure of the number of moles in A is obviously m upon m, where a small m is the mass given. It is given as I think, yeah, this one, and at this side pressure is P dash, let's suppose it is PB, initial pressure, into volume is V naught, temperature is T naught, and number of moles NB is, let's suppose, MB into MB upon M. So we can equate the value of gas constant R, and we can write down that that P naught, in fact P V naught upon N A into T naught will be equal to PB into V naught upon NB into T naught. So PB will be equal to NB upon NA into P, and NB upon NA will be equal to mass of gas in B upon mass of gas in A into P. First equation. Now finally the volume of gas A is equal to V naught by 2, and the volume of gas B will be equal to 3 V naught by 2. The process occurring in gas A is adiabatic process, so we can write that P initial of gas A was P, volume was V naught to the power gamma, gamma is given as 3 by 2, is equal to P final of the gas A will be PA, or we can say that P final A into final volume of A is 3 V naught by 2. In fact, final volume of A is V naught by 2, yeah, to the power 3 by 2. So we can say that P final of gas A will be equal to 2 to the power 2 by 3. In fact, 2 to the power 3 by 2 into P, which is 2 root 2. So P final of gas A will be 2 root 2 P, and obviously P final of gas B will be same because finally they are in equilibrium and their cross section area are equal. And for gas B, this is isothermal process, so for B we will use the equation P1 V1 will be equal to P2 V2. So initial pressure of gas B was PB and volume was V naught, and finally its volume is 3 V naught by 2 and pressure is PA final, which is 2 root 2 P into 3 V naught by 2. So you can see that PB will be 3 root 2 P, and we have already used this relation that PB upon P is MB upon M. So 3 root 2 will be equal to MB upon M. So MB will be equal to 3 root 2 M. So the correct option will be B. And now we have to find out the change in internal energy of gas in cylinder A. So the change in internal energy of the gas in cylinder A is obviously we can see that delta U will be equal to N CV delta T, and we know that the gas A, now let us see CV for the gas is it is given that gamma is 3 by 2, so CV is R upon gamma minus 1, so it is R upon 3 by 2 minus 1, so it is 2R, and the T initial of gas A was T naught, and T final of gas A can be calculated by using the final temperature formula. So we can say that PA VA by TA will be equal to PA final VA final upon TA final. So PA was initially P, VA was V naught, TA was T naught, and PA final is 2 to the power 3 by 2 into P, 2 to the power 3 by 2 into P into VA final is V naught by 2 and divided by TA final. So cancelling out this, so TA final will be equal to 2 to the power 1 by 2 into T naught, which is TA final will be equal to root 2 T naught. So delta U will be equal to positive, and N is the number of moles, which would be M upon M, or you can use it as N. CV is 2R, and delta T is root 2 minus 1 into T naught. Now we have to find out the value in terms of P naught into PV naught. So we can say that PV naught is equal to nRT naught. So nRT naught is PV naught, so delta U will be equal to 2 into root 2 minus 1 into P naught V naught. So delta U will be option number B. Now the work done by the gas in the cylinder B and work done WB and work done by the gas in the cylinder A, WA, will be related as. Now you know that there is no atmosphere in the surroundings, and therefore this gas B is doing the work done against A. So the work done by A will be equal to minus of work done by B. And what will be the final compressive force acting on the rod in equilibrium? So when this rod will be in equilibrium, you can see that from both sides pressure will be same, and pressure will be equal to 2 to the power 3 by 2 P. So 2 root 2 P, and force will be 2 root 2 P into area. So 2 to the power 3 by 2 into P into area is S. So option C is correct. Now let's move on the next question. In this question, you can see that there is an ideal gas which is between these two pistons at NTP, normal temperature and pressure. The walls of the cylinder is adiabatic, and this piston is connected with a spring, and both the pistons are light, which is they are massless, and the area of cross section of the cylinder is 27 centimeter square, and initially spring was relaxed and both the pistons were in equilibrium. The value of K for the spring is 3700 Newton per meter. Area of cross section is this, and the lower, if we are moving this lower piston into upward direction by a distance of h by 2, where h was the initial length of the gas column, then it is observed that the upper piston moves up by a distance of h by 16 till equilibrium is attained. Now gamma is 1 by 1.5. We have to find out the value of h, and also we have to find out the final temperature of the gas. So we know that this is a adiabatic process, and in adiabatic process we know that P1 V1 to the power gamma, which is 3 by 2, is equal to P2 V2 to the power gamma, which is 3 by 2 in this case. And initially the pressure of the gas was P naught. So P naught and volume was A into H to the power 3 by 2 is equal to P final, and the final volume V final will be, this is V final will be A into H was the initial height minus H by 2 is the distance moved by this piston in the upward direction. And you can easily see that if this piston will move in the upward direction, then the volume of gas will decrease. So we have used a negative sign, and as this piston will move in the upward direction, the volume of gas will increase. So it would be plus H by 16. So this will be equal to 9H by 16. So Vf will be A into H into 9 by 16. So we can use that P naught H A to the power 3 by 2 will be equal to P final into 9 by 16 to the power 3 by 2 into H A to the power 3 by 2. So cancelling this, P final will be equal to 16 to the power 3 by 2 is 64 and 9 to the power 3 by 2 is 27. So it would be 64 by 27 of P naught. Now this is the final pressure which we have calculated, and we can see that obviously the final pressure P final will be equal to P naught plus Kx by area. So P final will be equal to P naught plus K is 3700, X is H by 16, which is the distance moved up by this cylinder, this piston, and area is 27 into 10 raised to power minus 4 because it is in centimeter square. So P final is 3700 H by 16 into, let us use it like that, let us write it down as 37 into 10 to the power 6 H by 16 into 27 is equal to P final is 64 by 27, 64 by 27 P naught minus P naught. We have shifted this P naught on the other side of the equal to sign. So this will be 37 into 10 raised to power 6 H by 16 into 27 is equal to 37 P naught by 27. So cancelling out this, and we know that P naught is 10 to the power 5, so H will be equal to 16 by 10, so H will be equal to 1.6 meters. Okay, now we also have to find out the final temperature of the gas. So we know that T initial V initial to the power gamma minus 1 is equal to T final V final to the power gamma minus 1. Now T initial was 300 and V initial of the gas was equal to AH. Okay, and this is AH, and gamma minus 1 will be equal to 1 by 2, and T final is TF into V final is 9 by 16 of AH to the power 1 by 2. So T final will be equal to 4 by 3 times of 300, so it would be equal to 400 kelvins. So the correct answer is 400 kelvins. Now we move on the next question. In this question you can see that there is a adiabatic cylinder, and there is a movable piston which is also adiabatic, and this piston can move freely inside this cylinder. There is 1 mole of an ideal monatomic gas that is enclosed at this side of the cylinder, and the mass of the piston is m, and the mass of the complete cylinder including this gas is 4m, and this a mass, a point mass m is moving with a speed of v, strikes this piston elastically, and then this piston starts to compress this gas. We have to find out the change in temperature of the gas. So first of all, you can see that as this collision is elastic, so what we can say that velocity will interchange, and this piston will also start to move with velocity v after collision. So just after collision this ball will stop and this piston will start to move with velocity v. And you can imagine the situation that initially this gas will be compressed, and this gas will apply the extra pressure on the this chamber, and it will start to move, and this gas will retard this piston, and this gas will accelerate the chamber. So a point will come when this system, piston and the chamber will attain a common velocity, and that common velocity will be 5m V common, and it would be equal to mv. So V common will be equal to V by 5. This is the common velocity. Now initial kinetic energy was half mv square, and final kinetic energy is half mass is 5m and v is v by 5, so v square by 25. So final kinetic energy is mv square by 10, and the change in kinetic energy delta k is half mv square minus 1 by 10 mv square. So this change in kinetic energy will be 2 by 5 mv square. Now you can imagine that heat exchanged will be 0 because this is a adiabatic cylinder, and the change in kinetic energy, which is 2 by 5 mv square, will be utilized into the work done in compressing the gas, and work done will be equal to the negative of heat, negative of change in internal energy, because dq is 0. So we can say that dw will be equal to minus of du, and this work done will be negative because this work is being done against the gas and gas is being compressed. So the change in internal energy will be positive, and it would be NCV delta T. So CV is 3 by 2 R. So 2 by 5 mv square is equal to, N is 1, and this is 3 by 2 R delta T. So delta T will be equal to 4 by 15 mv square by R. So the correct answer is this, change in temperature. Now